All right, for this first one, anytime you have a more complicated ones like these, you will want to do the numerator as much as possible, the denominator as much as possible, and then simplify numerator to denominator, okay? So my first rule that I would probably apply here is this power to a power. So I would take each one of these and raise it to that -2. And when you have a power to a power, you multiply. So I have x to the 3 to the -2. So I'm going to multiply that 3 and -2 and get x to the -6. And then I'm going to multiply the -4 and the -2 and get y to the +8. All right? And I have that over x to the -2, y to the -1. So when I say simplify, I mean you only have one of each type of base, okay? I only have one type of x in the numerator. I only have one type of y in the numerator. That is simplified. Obviously, we can do more with this, but I can't simplify across anymore, and I can't do anything on the bottom at this point. So now I'm going to go top to bottom. I'm going to simplify the x's top to bottom and the y's top to bottom. And so when I do that piece of it, I'm going to use my subtraction. So I'm going to say x, since it's top to bottom, I'm going to subtract -6 minus a -2, and y, 8 minus a -1. You just subtract those. All right? -6 minus a -2 is plus a positive, so it's x to the -4. 8 minus a -1 is plus a positive, y to the 9th. And then my last step is to make sure that I don't have any negative exponents. Well, I currently do. This is a negative exponent. That negative reciprocates it. By that I mean if it's in the numerator, it goes to the denominator. If it's in the denominator, it goes to the numerator. These are both in numerator type positions because I don't have a denominator. So since they're both in numerator positions, the y is going to stay. It's a +9. The x is going to go to the bottom as a 4. And that's how we get this answer right here. Y to the 9th over x to the 4th. Make sense? All right, let's look at 44. All right, for this one, I'm going to do the same thing. I'm going to simplify my numerator and then see if I can simplify my denominator and then go top to bottom. So the first thing I notice is I have this group, power to a power here, a to the 3 squared. So I'm going to say 3 times 2, that's a to the 6th. B is technically to the first. 1 times 2 makes that b squared. I have this other a here, and then I have b to the 0. What is anything to the 0 power? Just 1. So this is like times 1. Not a to the first, just the number 1, okay? And I have that over the a squared b to the -3. All right? Then I'm going to see, can I simplify any more? Well, the numerator still has multiple a's as bases. So I need to simplify those, all right? This is technically an a to the first. I am multiplying like bases. A to the 6th times a to the 1st power. I have a to the 7th power. A to the 7th power. And then I have this b squared, and you really don't have to put the 1 if there's other things in the numerator. That's the coefficient. But remember, if the coefficient is 1, you can just leave it off because it's like 1x or x, those are the same thing. The denominator just has 1 base of an a and 1 base of a b. So we're good. So now that I've simplified those as much as possible, I'm going to go top to bottom. All right? So I'm going to say, for my a's, I have 7 minus 2. For my b's, I have 2 minus a -3. Well, 7 minus 2 is just a 5. 2 minus a -3 is also just a 5. They're both positive. Nothing moves. I'm done. All right, so this is all review from Algebra 1. And what I love about solving inequalities is we've already covered solving equations, and they're very, very similar. The main difference is that an inequality actually means not equal to, right? So there is a comparison that happens between two things. Two things can be equal. Two things can be not equal. And in that not equal, you have options. A can be bigger than B. B can be bigger than A, right? And so these are all the types of symbols that you use when things are not an equation. These are types of inequalities. But solving inequalities works very much the same as solving an equation. If you don't remember the symbols, just remember that they point to the smaller guy. But it's always like you're reading from left to right. So people confuse these, which one's less than, which one's greater than. Think about the way we read in English, okay? In English, we read from left to right, okay? And so if I have this first symbol, the left side is smaller than the big side, that's less than. The left side is greater than the right side. Not equal to, that's exactly what it stands for. They don't equal each other. And then you have these two less than or greater than with the extra line under it. That extra line represents and also equal to. All right, so think of it as combining the greater than, less than with an equal sign. And they smushed them together and they got greater than or equal to, less than or equal to. These are the options. And you have this trichotomy property, which is something that you probably don't know the name of, but you've used it. And it means that when you are comparing two numbers, you have three options. One number is bigger than the other, one number is less than the other, or the numbers are equal to each other. These are the only three options when we're talking about real numbers, okay? And so that's what the trichotomy says. And of course you throw in the or equal to, but that still falls within one of those three. So when you're solving these, you really set them up very much like you would do an equation. Your goal is to get numbers to one side, variables to the other, multiply or divide to solve. Adding and subtracting is identical. If you add or subtract on both sides of an inequality, you do not change the inequality, all right? The multiplication division is a little kooky, right? If you multiply or divide by a negative, it flip-flops the sign, okay? And in Algebra 1, we kind of walk through why that happens. But as you multiply down the scale, you can see that as you multiply, when you get to negative, all of a sudden those numbers flip because now you're on the opposite side of the number line, okay? And so if you're greater than 1 on this side and you flip to the other side, then you're going to be less than, because on the left-hand side, what's your side? On the left-hand side of the number line, you are less than. On the right-hand side, you're greater than. And so if you were to flip sides, which is what a negative does, then obviously your sign should flip as well. And so that's the only difference. Adding and subtracting, identical. Multiplication with a positive number, identical. But if you multiply or divide by a negative, you have to flip-flop that greater than, less than sign. All right, so let's solve some of these. Look at example 1. They want us to solve 4x plus 12 is less than 8. Now, when you're solving an equation, you get one answer here. X equals this. When you're solving an inequality, you get a group of answers. And that's why there's a number line here, because this number line represents the group of answers that will make this true. All right, instead of one solution, you're going to have a whole set of numbers as a solution. So I'm going to take the 4x plus 12 less than 8. My first step here is going to be subtract the 12 over. Move everything that does not have a variable. So I'm going to move this over. All right. On the left-hand side, my 12s cancel. On the right-hand side, 8 minus 12 is negative 4. Now, I'm going to divide by 4. Am I dividing by a negative? No, I'm dividing by positive 4. It does not matter what that other guy is. It only matters what is with your variable, okay? So I'm dividing by a positive 4 here. My sign will not flip. My answer here is going to be that x is less than negative 1. I represent that on a graph by going to negative 1. If I am only less than, I have to indicate that it's not also equal to negative 1. So I indicate that by saying, okay, I need to do an open circle here, because even though that's where I start, I don't actually include him. If I included him or equal to, I would fill that circle in, indicating 1 is part of my answer. But 1 is not part of my answer. It is an open circle here. Everything smaller than 1. X is less than negative 1. Smaller than negative 1 is the left side of negative 1. And that's my answer here. Solves exactly the same. Look at example 2. All right. Example 2 is larger, but conceptually we're doing the same exact thing. My first step, if this were an equation, would be to distribute. That is my first step here. I'm going to take the 2 and I am going to distribute it through 2 times x plus 2 times 9. I am going to take the negative 6, don't forget the negative, and I am going to distribute that through negative 6 times x, negative 6 times 2. And then I'm going to write my greater than or equal to sign. Nothing on the right-hand side can simplify. My next step, if I were doing an equation here, would be to combine any like terms, simplify each side, okay? Remember, when you're simplifying the side, you don't change your signs. You do exactly what it tells you to do. The only time you change your sign is when you're adding or subtracting across, okay? So in this case, I have like terms. I have a 2x and a negative 6x. So I have a negative 4x. I have a positive 18 and a negative 12. That gives me a positive 6, greater than or equal to x minus 4. Both sides are as simple as I can get them. Variables on one side, numbers on the other, all right? So I'm going to move my x over, all right? And I'm going to move my 6 to the other side. So over here, the x's cancel on the left-hand side. The 6's cancel. I'm left with negative 4 minus 1. That's negative 5x. Bring down your greater than or less than sign. Negative 4 minus 6, that is negative 10. Now I have variables on one side, numbers on the other. What do I need to divide by? Now I am dividing by a negative, all right? This is the situation where I'm going to flip this. Negative 5 divided by negative 5 gives me an x. I need to flip that sign. He was greater than or equal to. He becomes less than or equal to, because I have just dividing by a negative makes me give the opposite answer. And so the opposite's going to jump you to the other side of the number line. So that greater than less than has to also flip when that happens, okay? Because I have flipped the opposite side of the number line. Negative 10 divided by negative 5 is positive 2. 2 is where I'm going to start. I go to positive 2 on my number line. It includes my positive 2. Since it includes my positive 2, I am going to indicate that this is part of my answer with a closed circle. All right? And is x smaller or bigger than 2? Smaller. So which side of my graph is smaller? The left. Yep, the negative side of it. All right? See how we're doing here? One more, and then I'm going to have you do some. One more, then I want you to do some. All right. Example 3. This is conceptually the same. There's 2 different examples for this guy. We have distribution like we did on the other one. But this is a little bit different, and you're going to see why this one's different. So I'm going to distribute my 3 through. 3 times negative 2x, 3 times 9 is less than, I'm going to distribute that negative 2. Negative 2 times 3x, negative 2 times 4. Variables on one side, so I'm going to move my 6x over. And then numbers on the other. I'm going to move my 27 over. All right. Negative 6x plus positive 6x gives me what? 0. 0x, but it's 0, right? Because 0 times anything. So this gives me 0. All right. Negative 8 minus 27 gives me what? Negative 35. 0 is less than negative 35. Is that a true or a false statement? That is false. Would you rather have no money or owe somebody $35, right? Like 0 is definitely bigger than negative 35, not smaller. I have come up with a false statement. This is false. When you have a false statement, what that tells you is there is no x that will ever make this a true statement. So if I'm asking you, hey, what x's make this a true statement? You're going to say, no x's make this a true statement. And the way you indicate to me that no x's will make this a true statement is you say this little guy right here, which represents the empty set. I'm saying what set of numbers makes 0 less than negative 35? You're going to say no numbers make 0 less than negative 35. And you can tell me no numbers by saying no solution, just like that. You can write the words no solution. That means there are no numbers in this solution. Or you can do your brackets with nothing in them. All 3 of these indicate there are no answers to this question that make it true. Okay? So that's one type of problem you can run into with these, okay? No solution. No numbers will ever make that statement true, and that's what you're telling me. All right? Look at the next one, which is B. Same thing here. We're going to distribute my 5 through. 5 times 3x, 5 times 6, minus 15x, greater than or equal to 0. Combine my terms, simplify my left-hand side. 15x and negative 15x. Once again, we get 0, right? Plus 30 is greater than or equal to 0. I can combine more like terms. 0 and 30 give me 30 is greater than or equal to 0. When is 30 bigger than 0? Always, right? So if I said, what set of numbers would make this true? You would say all numbers make that. I can't give you a number that doesn't make that true, right? So I now have a true statement here. All my variables are gone, and I have just come up with a true statement, okay? A true statement, which means every single x that you plug in will make this a true statement. The way you indicate every single x is you can do a couple things. You can say that guy right there. He stands for the set of all real numbers. You could say all real numbers, right? On the number line, what would it look like? Well, it would look like the whole entire number line, right? The whole number line makes this guy true, okay? And so if you get a false statement, you need to somehow indicate by some empty set notation that the answer doesn't work. If you get a true statement, you need to indicate by one of these that all numbers work. One way or the other, you need to tell me. All right, so you can take separate inequalities and put them together with these compound conjunction and disjunction. This should sound familiar from geometry. We did conjunctions and disjunctions in geometry. You also do them in English, by the way. A conjunction in a sentence puts two independent thoughts together, right? So if you ever have Miss Amy say, hey, this is a comma slice, it's because you forgot your conjunction, right? You just threw sentences together, put a comma in there, and forgot this little joining words that you need to put those two sentences together. Same is true for math. You're putting two separate concepts together into one, okay? And so what this does is this says, I need to see one of two things. I need to either see where these two separate guys overlap. That is my intersection. In set theory, it looks like an upside down U. In conjunction disjunction for inequalities, it looks like an upside down V, okay? But this is where they overlap, conjunction. Disjunction is or. It means you can take these two separate thoughts and their entire answer is the answer. No matter if they cross over, if they don't cross over, it does not matter, okay? With intersection, it matters. They must cross over, and I only want where they cross over as my answer. But you're doing the same thing. You're doing two separate independent thoughts, and you're putting them together with either an and or an or. So let's look at the first one. Sometimes they will write the word and, or they will write the word or. In this case, they simply said and. You are going to solve the left guy independently. You're going to solve the right guy independently, and where they cross over is your answer. All right? So we're going to do this exactly the same way. We're going to subtract our 9. We're going to get 5x is less than or equal to 15. We're going to divide by that 5. And we get x is less than or equal to 3. We're done with the left-hand side. We're going to move on to the right. We're going to add our 7. We have negative 3x is greater than 21. Divide by that negative 3. We get x. Flip this guy is less than negative 7. All right? And this is and, which means I need to know where these guys cross over. So when I want to know where they cross over, my answer is going to go on a number line. And so what I typically do is I kind of do it somewhere else and then put my final answer on the number line. So I'm going to drop below it, and I'm going to say x is less than or equal to 3. So I'm going to go to this 3 closed circle. Less than goes this direction. X is greater than negative 7. Open circle, because I don't include it, and everything bigger. So then I'm going to graph where they cross over. Where they cross over. Oh, less than, sorry. Was that your question? Yeah. There we go. That way, all right? Less than. So then I'm going to graph only where they cross over. Well, they only cross over starting here and going that way. So that means none of this is part of the solution because it doesn't cross over, all right? It also means that negative 7 is not part of the solution because it's part of my less than or equal to 3, but it is not part of my less than negative 7. So the only place that's actually going to be part of my answer is this going that direction. So my only answer here is that x is less than negative 7. That's the only place they actually crossed over, okay? That's the only place they crossed over. This is another way to write and. You'll notice there is no word and there is no notation, but they've shoved it all together into one. And what they're really saying is they're saying 8 is less than 5x minus 7 and 5x minus 7 is less than 18. All right? And so there's actually two ways to solve this guy. I'll bring this down here. The first way is to leave it alone and just take everything from all three parts and try to get your variable on the inside. All right? So if I do that, I'm trying to get my variable all alone inside the middle, which means I take out everything that doesn't belong with him. So I have this negative 7. I need to add it to all three parts. I need to add it over here on the left and on the right if I added it in the middle. It is going to cancel in the middle. On the left, I will have 15. Bring down your less than. Bring down your other less than. And then over here, I have 25. Okay? What else do I need to get x all alone? What do I need to do here? Divide by 5. Well, I have to divide by 5 in the middle. I have to do that on the other two parts. Divide by 5, divide by 5. On the inside, it cancels. I have 15 divided by 5. I have just my x, which is what I want. I have 25 divided by 5. Now, when you do it this way, it's very easy to see what x will look like on a number line, isn't it? I'm going to be bigger than 3 and smaller than 5. And I don't include either of my points. And so when you do it this way, it's kind of easy to see that my graph is going to be starting at 3, ending at 5, and everything in between it, okay? So if you solve it like this, you kind of get a picture visually of what your answer is going to be. But if you don't like solving it this way, you can solve it as two different ones. All right? And you do exactly what we did. You would add your 7 over. You would get 15 is less than 5x, and you would get that x is greater than 3. If you did it over here, you would add your 7. You would get 5x is less than 25, and you would get x is less than 5. And when you graph those, greater than 3, less than 5, you'll see the same crossover section. All right? Those are your ands. They can write it out. They can put them together. We're going to do one where they use, instead of the word and, the symbol for and. But your ands could be either pushed together or two separate ones with the word or symbol for and. All right? Your disjunctions are ors. You will never see an or put together because that automatically means and. Anytime you have an or a disjunction, you will see either the word or you will see the symbol for the word or, the V, okay? You will never see an or put together like this. That's only for and. So if you look at page 35 in your books, example 3, you will always solve the ors as two individual problems, all right? All right, let's look at example 3. We have an or. 9x plus 6 is greater than 60, or negative 2x plus 7 minus 3x is greater than or equal to 11. So for this one, I'm literally going to solve these individually. I'm going to take this first one. I'm going to solve it. I'm going to take the second one, and I will solve it by itself as well. And so I'm going to do my same process. Subtract your 6. 9x is greater than 54. Divide by 9. X is greater than 6. Over here, do what I would do. Distribute. All right? Combine my like terms. So I have a negative 2, negative 3. Move my numbers over. And then I'm going to divide. Now remember, same rules apply. What happened here? I divided by what? A negative. This guy has to flip. So I have x is less than or equal to negative 5. But this guy is an or. So let's look at what happens on my number line with him. All right. So let's look at what happens when I put this on a number line. Okay. Now with an and, specifically I wanted where they crossed over. With this one, I am going to just graph them individually. I have x is greater than positive 6. Open circle, because this does not include it, and bigger. This other piece of it, less than or equal to negative 5, close circle, and less than. They do not cross over, but that entire graph is my answer. So when you have these, your entire thing is your answer. Your entire thing is your answer. All right? Look at So this is the last way they could write these. And what you have to do is you just have to remember what the symbols are. So if you see this one, they could have easily also have written the word and in between it. If you see this one, they could have written the word or in between it, okay? And just like on your regular inequalities, you can get a no solution, all right? And we're not, for time's sake, we're not going to go through all of them. But if you have an and that does not cross over, so let's say you get an and one's going one direction and one's going the other, and there is no place where they cross over, you could get a no solution, all right, for this. With an or, you can get an all real numbers. Let's say one of them starts here and goes that direction, and one of them starts here and goes that direction. If it's all the numbers, not where they cross over, this is going to take the entire number line. And so you can get something like this for an or. So and could have a special case that has no solution where they don't cross over. An or can have a special case where it's all real numbers because they do cross over. All right? And so just keep in mind what your answer is.